CS3351 Digital Principles and Computer Organization. Topic is Instruction Set Architecture, presented by Devi Visalakshi, Assistant Professor of CSE Department, Rohini College of Engineering and Technology. Instruction Set Architecture. An instruction set architecture is part of the abstract model of a computer that defines how the CPU is controlled by a software. The ISA acts as an interface between the hardware and the software, specifying both what the processor is capable of doing well as how it gets done. Two types of instruction set computers are CISC or ISC. The ISA of a processor can be described using 5 categories: operand storage in the CPU, number of explicit name and operations, operand locations, operations type and size of operands. The most common types of ICAs are stack, accumulator, as well as general purpose register. Stack. The stack operands are implicitly on top of the stack. Accumulator. One operand is implicitly the accumulator. General purpose register. All operands are explicitly mentioned. They are either registers or memory locations. The 8086 has many instructions that use explicit operands, although it has a general register set. The 8051 is another example. It has 4 banks of GPRS, but most instructions might have a register as one of its operands. Stacks. Advantages: simple model of expression evaluation, short instructions. Disadvantages: a stack cannot be randomly accessed. This makes it hard to generate efficient code. The stack itself is accessed every operation and becomes bottleneck. Accumulator advantages: short instructions. Disadvantages: the accumulator is only temporary storage, so memory that is highest for this approach, GPRS. Advantages: make code generation easy. Data can be stored for long periods in registers. Disadvantages: all operands must be named, leading to longer instructions. Reduced Instruction Set Computer, that is RISC. RISC stands for Reduced Instruction Set Computer. The ISA is composed instructions that have exactly the same size, usually 32 bits. Thus, they can be prefetched and pipelined successfully. All ALU instructions have 3 operands, which are only registers. The only memory access is through explicit load store instructions. The C is equal to A plus B will be assembled as. So, if you want to write the instructions for C is equal to A plus B, means first you have to write load R1 comma A, load R2 comma B, add R3, R1, R2, store C comma R3. Complex instruction set architecture. The main idea is that this single instruction will do all loading, evaluating and storing operations, just like a multiplication command will do stuff like loading data, evaluating and storing it, hence its complex memory locations and addresses. The memory consists of many millions of storage cells. Each of it can be store a bit of information having the value 0 or 1, because a single bit represents a very small amount of information. Bits are seldom handled individually. The usual approach is to ideal with them in groups of fixed size. For this purpose, the memory is organized so that a group of n bits can be stored or retrieved in a single basic operation. Each group of n bits is referred to as a word of information, and n is called the word length. The memory of a computer can be schematically represented as a collection of words. Modern computers have word lengths that typically range from 16 to 64 bits. If the word length of a computer is 32 bits, a word can store a 32-bit signed number. or 4 ASCII encoded characters, each occupying 8 bits as shown in the figure. The signed integer as well as 4 characters. A unit of bits is called a byte. Machine instructions may require one or more words for their representation. After we described instructions at the assembly language level, accessing the memory to store or retrieve a single item information, either a word or a byte, requires distinct names and addresses for each location. It is customary to use numbers of 0 to 2k minus 1 for some suitable value of k as the addresses of successive locations in the memory. Thus, the memory can have up to 2k addressable locations. The 2k addresses constitute the address space of the computer. For example, a 24-bit address generates an address space for 224 locations. The number is usually written in 16 mega, where 1 mega is the number 220. A 32-bit address creates an address space of 232, that is 4 giga locations, where 1 is 230. Other rotational conversions that are commonly used are K, that is kilo, for a number 210 and tera for the number 240. Byte addressability. A byte is always 8 bits, but the word length typically ranges from 16 to 64 bits. It is impractical to assign distinct addresses to individual bit locations in the memory. The most practical assignment is to have successive addresses refer to successive byte locations in the memory. This is the assignment used to modern computers. The term byte addressable memory is used for assignment. Byte locations have addresses 0, 1, 2. Thus, if the word length of the machine is 32 bit, successive words are located at addresses 0, 4, 8, which each word consisting of 4 bytes. There are two ways that byte addresses can be assigned across words Big Endian and Little Endian. So this is the representation of Big Endian assignment as well as Little Endian assignment. Memory operations. Both program instructions and data operands are stored in the memory. To execute an instructions, the processor control units circuits must cause the word containing the instruction to be transferred from the memory to the processor. Operands and results must also be moved between the memory and the processor. Read operation. The read operation transfers a copy of the contents of a specific memory location to the processor. The memory contents remain unchanged. To start a read operation, the processor sends the addresses of desired location to the memory and the request that is contents to be read. The memory reads the data stored at the addresses and sends them to the processor. Next we can see the write operation. The write operation transfers an item of information from the processor to a specific memory location, overwriting the former contents of the location. To initiate a write operation, the processor sends the addresses of the desired location to the memory together with the data to be written into the location. The memory then uses the addresses and data to perform write.